Hi, my name is Lucas Brewster, and I'm the team lead for the Carleton Planetary Robotics team. From Carleton University in Ottawa, we're a team of undergraduate students with the goal of annually designing, building, and programming a simulated Mars rover for competing in international competitions. Since August, the team has been working hard to make this year's design a reality, and it's my pleasure to introduce to you Waldo.
This year's rover has 3 main configurations using different subsystems optimized for each task.
The rover uses 6 12-inch custom sheet aluminum and spring steel wheels to move. The spring steel is coated with a layer of rubber to provide traction on tough terrain. Each wheel uses a VEX DC motor connected to an 81:1 planetary gearbox. This gives us a top speed of 4.2 meters per second and the ability to scale 30-degree slopes. The rover chassis features independent aluminum channel connected to air shocks and drives using skid steering. This system allows us to scale stairs and cross over obstacles 12 inches tall.
The rover uses a sheet metal and carbon fiber arm for the retrieval and equipment servicing tasks. The arm uses 3 harmonic drives to move the turret, shoulder, and elbow, and is capable of lifting 6 kilograms at a reach of 1.2 meters. It also gives the rover the capability to do push-ups. A dexterous, custom-designed gear system controls the pitch and roll of the claw. Together, the 5 degrees of freedom provides us with precise control for manipulation during the equipment servicing tasks and retrieval tasks.
The science module mounts to the front of the frame and uses an earth auger to move dirt through a carbon fiber sleeve. The science module then inserts a sensor into the hole it created to measure soil moisture and temperature.
This year, the electrical team aided the mechanical team in reducing total rover mass by changing from a 12-volt to a 24-volt power architecture. This change allowed us to run thinner wire gauge throughout the rover, reducing our total copper mass and aiding in cable management.
In order to be better prepared for the aspects of the competition that will take place out of line of sight, we have transitioned our communication from 2.4 gigahertz to 900 megahertz. This was made possible through the use of a sector antenna at our base station and an omnidirectional antenna on our rover's mast. Another main focus of Elect Team was the decoupling of electrical and mechanical manufacturing. This was done through the use of 3 polycarbonate boxes which house clusters of electronics. Our battery box contains e-stop, current sensing, and regulation. Our electronics box houses regulation, computation, locomotion arm train, and sensor interfaces. Our science box contains our science center interfaces and arm locomotion. Once the frame was assembled, we were able to slide our boxes in and secure them.
We've also reduced our battery mass by approximately 3 kilograms while maintaining our previous design's capacity by changing from a lithium iron phosphate to a lithium polymer chemistry. We've accounted for the increase in battery chemistry volatility by introducing an isolated emergency stop system powered by an independent battery.
Octa-core Odroid XU4s are used to control the major subsystems of our rover. STM32 embedded microcontrollers will read data from the various sensors on the rover, including the GPS, the IMU, and various sensors for the science cache task. The GPS and IMU measurements are also used to control the orientation of our directional antenna, to ensure that the antenna will track the position of the rover as it moves through the course. Our interface has been loaded with satellite imagery of our competition and training sites. GPS and IMU data will be transmitted to the user interface, where it is used to display the current position and heading of the rover on the map. Our navigator can place markers on the map to plan routes and goals, which are shared with the driver to provide unambiguous planning. The operator is able to dynamically turn cameras on and off, as well as to control the resolution, frame rate, and quality of the MJPEG streams. Autonomous navigation is made possible with a stereo camera, which contains 2 cameras separated by a known distance. The overlay of these images is used to compute a disparity image and depth map for the environment, allowing for obstacle detection and avoidance as the rover navigates towards its target.
Using dirt samples from the area in and around MDRS, we'll be able to calibrate our onboard temperature and soil moisture sensors while developing a baseline for in-lab tests of pH, ammonia acid right-left-handed ratio, salt content, grain size, and mineralogy breakdown. Additional mission planning used to create geology reference guides, along with having science members within the operations station, will allow for effective site selection, aiding in the quality of samples and data that can be analyzed. Onboard the rover, we'll be carrying a suite of gas sensors, which will measure hydrogen, methane, and LPG. Known as sense-seeking, we can analyze the atmospheric composition of our sample site, further contributing to the search for water and suitability for supporting life.
During operator training, we were running several missions with anticipated failure modes, such as losing communications, motors, and various sensors. This will ensure that our operations team have backup plans in place and know to adapt the system to ensure mission success.